This is my Precalculus course. Today we're going to continue to learn sequences in series. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous class, we learned how to find a term of an arithmetic or geometric sequence. And we also learned how to find the sum of the first n terms of an arithmetic or geometric sequence. Well, now we're going to do some more problems on those types of sequences. These are just some different problems that you're going to see. If the third term of an arithmetic sequence is 16 and the seventh term is 28, what is the 10th term? So you don't have to do this, but just to help us visualize what the problem is asking, I'm going to write the number of each term. So we're told that the third term is 16 and the seventh term is 28, and we're looking for the 10th term. We're also told that this is an arithmetic sequence. So what that means is we're going to add some constant number to get to the next terms. So the fourth term is going to be the third term plus the common difference. And the fifth term is going to be the third term plus 2 times the common difference, because we already added d once to get to the fourth term. We have to add it again to get to the fifth term. And the sixth term is going to be the third term plus 3 times the common difference. And to get to the seventh term, we have to take the third term and add 4 times the common difference, and that should be equal to 28. So all we have to do is solve that equation to find the common difference, and we'll use the common difference to help us find the 10th term. So if we subtract 16 from both sides, we get 12. Divide both sides by 4, and we get 3. So the common difference is 3, and we don't have a lot of room to write over there, so I'm going to move to the left. And so to find the 10th term, which is what we're looking for, I'm going to start with the 7th term because that's closest. And again, you don't have to write all this out. You do have to show the equation that you're using, but you don't have to write all these numbers and all these expressions here. This is just to help you understand how to do the problem. So the 7th term, we'll write that again, that's 28. And to get the 8th term, we're going to add 3. And then to get to the 9th term, we'll add 3 again. And to get to the 10th term, we'll add 3 again. So we get to 37. The 10th term is 37. So that's the general principle for how we're going to do these problems. So let's try another problem. We're told that the 8th term is 0.4 and the 20th term is negative 12.8, and we're looking for the 13th term, which is going to be somewhere in the middle, somewhere around here. So this is an arithmetic sequence, we're told, so we're going to add the common difference to get to the 20th term. So if we start with the 8th term and then add the common difference 12 times, we should get the 20th term, the value of the 20th term. So how did I know to add this blue 12? Well, 20 minus 8 is 12, so that's how many times you have to add it to get to the 20th term. So if we solve this equation, we get negative 1.1. So now we can use that common difference to help us find the 13th term. So to find the 13th term, we can either start with the 20th and then go backwards by actually adding 1.1, or we can start with the 8th term and subtract 1.1 to going forward to get to the 13th term, because the common difference is a negative number. So the 8th term is closer, so I'm going to start with the 8th term. So we have 0.4, the 8th term, and I'm going to move that down here. And then we're going to subtract 1.1 to get to the 9th term, subtract it again to get to the 10th term, subtract it again to get to the 11th, subtract it again to get to the 12th, and subtract it again to get to the 13th. So if we do the math on that, 1.1, negative 1.1 times 5 is negative 5.5, and then add that to 0.4, and we get negative 5.1. So the 13th term is negative 5.1. And we're going to have to move this over a little bit. Move this stuff up. So the 13th term is negative 5.1. Again, you don't have to write all this stuff out. I do want you to show some work. And we can't really even fit that on the page, so we don't really need that. Okay, so I want you to try number 3, and when you come back, we'll do it together. Okay, we're back. So we know that the 4th term is 19, and the 10th term is negative 11. And we're trying to find the 14th term. So how many times do we add the common difference to get to the 10th term? Well, that's just 6 times. 10 minus 4 is 6. So the 4th term plus 6 times the common difference should be equal to the value of the 10th term, which is negative 11. So if we solve this equation, we get negative 5. The common difference is negative 5. So I don't have a lot of room at the right, so I'm going to move this over here. Now we're closer to the 10th term, so we're going to start with the 10th term, which is negative 11. And then we're going to subtract 5 to get to the 11th term, and subtract it again to get to the 12th, and again to get to the 13th, and again to get to the 14th. So that will give us negative 31 for the 14th term. So if you got that one right, excellent. Okay, so I want you to try number 4, and when you come back, we'll do it together. Okay, we're back. So we're told that the 6th term is 5, and the 21st term is 10. And we're looking for the 4th term, which is actually going to be to the left. We're looking for this term over here. So how many times do we add the common difference to get to the 21st term? Well, that's just going to be 15. So the 6th term plus 15 times the common difference is equal to the 21st term. So 21 minus 6 is 15. That's how we got that blue 15. We're adding the common difference 15 times to get from the 6th term to the 21st term. So if we solve, we find that the common difference is 1/3. So obviously it's going to be easier to start at the 6th term and then go backwards to get to the 4th term. So the 6th term is 5, and then we're going to add negative 1/3 and negative 1/3 again to get to the 4th term. Now the reason we're adding negative 1/3 is because we're going backwards. The common difference is positive, so to go to the right you would add 1/3, but if you're going to go backwards you would subtract 1/3. And if we do that, we end up with 4 and 1/3. That is the 4th term. So if you got that right, excellent. Okay, so now we're going to do very similar problems, but with geometric sequences rather than arithmetic sequences. And so we're told if the 5th term of a geometric sequence is 6 and the 7th is 54, what is the 8th term? So we know that the 5th term is 6, and we want the, well, we know that the 7th term is 54, and we want the 8th term. Again, you don't have to write all this out necessarily. Now, this is a geometric sequence, so instead of adding some constant number to get to the next terms, you're going to be multiplying some constant number to get to the next terms. So we call that constant number the common ratio. So the 6th term is going to be 6 times the common ratio. The 7th term, I guess I'll move these a little closer. The 7th term is going to be 6r, which is the 6th term, times r again to get to the 7th term. So that's going to be 6r squared. So 6r squared should be equal to whatever the 7th term is, but we know the 7th term is 54. So now we're going to divide both sides of the equation by 6, and we get 9. And notice up here in blue, it says assume that the common ratio is positive. So that means that r has to be positive 3, not negative 3. So now that we know r, the common ratio, we can use that to help us find the 8th term. So we're going to start with the 7th term because that's closer. 7th term is 54. And to find the 8th term, all we have to do is multiply by r. And so 3 times 54 is 162. So as you can see, this is very similar to what we did in the previous problems. The only difference is we're using geometric sequences in these types of problems. So let's try another one of these. If the 23rd term of a geometric sequence is 1/9 and the 26th term is 24, what is the 20th term? So we know that the 23rd term is 1/9. And the 26th term is 24. And we're looking for the 20th term, which is over here. So if you're going from the 23rd term to the 26th term, we have to multiply by r 3 times. And I'll just write this out. So 24th term and 25th term and then 26. So the 23rd term is 1/9. The 24th term is going to be r times 1/9. And the 26th term is going to be r squared times 1/9. And the 26th term is going to be r cubed times 1/9. So we take the 23rd term and multiply it by r 3 times to get to the 26th term. So what that means is that 1/9 times r cubed has to be equal to 24. If we multiply both sides of that equation by 9, 24 times 9, we get 216. So r cubed is 216. And if we cube root both sides, we get 6. And in this case, 6 has to be positive. If you're going from the 23rd term to the 26th, then you have a positive and still a positive for the 26th term. That means that the common ratio has to be positive, because we're starting with a positive, and if you multiply by a negative, this would be negative. Multiply by a negative, this would be positive. And multiply by a negative, this would be a negative number, but it's not, which means that the common ratio has to be positive. Okay, so we know the common ratio is 6. So what we're going to do is take the 23rd term, and then we're going to go backwards. I'm going to go to the 22nd, and then 21st, and then 20th. So the 23rd term we were given is 1/9. And because we're going backwards, we're not going to multiply by r, we're going to divide by r. So 1/9 divided by r is 1/9r. Then we have 1/9r squared, and then 1/9r cubed. So we don't have to write the r's out though, because we know that r is 6. So we're just going to take 1/9 and divide it by 6. And then divide it by 6 again. And divide it by 6 again. So you don't have to show the work this way. This is just one way to express what we're doing. Obviously I'm not focusing on speed here, because we're trying to show our work. So if we do the math on that, we see that the 20th term is going to be 1/1944. Sorry, that's so cramped there. So 1/1944. We can move this up a little bit. Okay, so now I'd like you to try number 7. Remember, we're dealing with geometric sequences now. So try number 7. When you come back, we'll do it together. Okay, we're back. So we know that the 6th term is -4. And we know that the 10th term is -64. And we're looking for the 9th term, which is somewhere around here. So that's the term that we're looking for. So this is a geometric sequence, so we're going to be multiplying by some constant. So how many times do we multiply the 6th term by the common ratio to get to the 10th term? Well, that's just going to be 4, because 10 minus 6 is 4. So if we take the 6th term and multiply by r 4 times, we should get the 10th term. Divide both sides by -4, and we have r to the 4th is equal to 16. And it tells us that r has to be positive, so it's going to be +2. And now that we have the common ratio, we can use that to find the 9th term. So we know that the 10th term is -64. We can start from there. We could start from the 6th term, but -64 is, or the 10th term is closer. So we'll start with the 10th term, which is -64, and then we'll take that and divide by 2. And why are we dividing? Because we're going in the opposite direction, just like we did over here. In this problem up here, we went forward. In this problem, we're going backwards, so we're dividing to get to the 9th term. And -64 divided by 2 is -32. Alright, so if you got that one right, good job. Go ahead and try number 8, and when you come back, we'll do it together. Okay, we're back. So we're told that the 2nd term is 27, and the 8th term is 1/27. And we're looking for the 10th term. So again, this is a geometric sequence. So we have to multiply 27 by some constant 6 times to get to the 8th term, because 8 minus 2 is 6. So the 8th term is going to be 27 times r to the 6th. That has to be 1/27. And let's divide both sides of that equation by 27. And we get 1/729. So if we 6th root that, we get 1/3. So the common ratio is 1/3. And we need the 10th term. So we can start with the 8th. and the 8th is 1 over 27. And then we're going to multiply that by 1/3 to get to the 9th. And then we're going to multiply that by that 9th term by 1/3. We can move this over a little bit. That's the benefit of having a digital notebook. So we're going to multiply by 1/3 again to get to the 10th term. So if we multiply, we get 1 over 243. So if you got that right, excellent. Okay, so those are just some different types of problems that you may see. Now, again, in the previous class, we learned how to find the sum of the first n terms of an arithmetic sequence and also a geometric sequence. But now we're going to learn how to find the sum of what we call an infinite geometric series. Remember, a series is a sum. And what this means is we're going to add an infinite number of terms. And technically that's not really correct because infinity is not a number, so we can't really say an infinite number. But the idea is that a sequence, like the sequence you see here, is actually, well, it doesn't end. It just continues indefinitely. That's what this ellipsis tells us. And in some cases, it's actually possible to add up all of the terms, even though it's a never-ending list. It's an infinite list. And I know that seems impossible, but if the common ratio of a geometric sequence is between -1 and 1, and what that means is it's got to be a fraction between -1 and 1, then the sum is equal to the first term in the sequence divided by 1 minus the common ratio. And we notate the sum as S subscript infinity. So I want you to get a picture of this information. And I want to explain real quickly here why that works. So let's say that R is equal to 1/2. And R squared would then be 1/2 times 1/2. And R cubed would be 1/2 times 1/2 times 1/2. And R to the 4th power would be 1/16. If you keep multiplying, R to the 5th would be 1 over 32. And notice that these numbers are getting smaller and smaller and smaller. When you multiply a fraction between -1 and 1 by another fraction between -1 and 1, you actually make the number smaller and smaller and smaller. So if your sequence has a common ratio that is a fraction, in the case of this first sequence we're going to learn here, notice that the numbers are approaching 0. So if the terms in a geometric sequence approach 0, then we can actually find the sum of all the terms, even though there's an infinite number of terms. And we do this with something called a limit. We use the concept of a limit, which is what calculus is based on. It's based on the concept of what we call a limit. So to show where this formula comes from, we're going to take our sum formula that we learned in the previous class. The sum of the first n terms of a geometric sequence is equal to this expression here. And we're going to change the form of this blue expression we're first going to take this a1 and multiply it up into the numerator. That's completely legal in math. Remember, that's just basic arithmetic. Then we're going to use the distribution rule. We're going to multiply a1 by 1, and then we're going to multiply a1 by r to the n. So we just use the distributed property. And then we're going to take this fraction and we're going to do what's called fraction decomposition. We're going to break that fraction into two fractions, and in order to see why that works, start over here, and you see we have a common denominator, and we're going to go backwards. So we're going to combine these two fractions with their common denominator to this, and you can see why these two expressions are equal. Instead of combining the fractions, we're just going in the opposite direction, and we're doing fraction decomposition. So we change this expression to this expression over here. Now, if we're going to try to add up an infinite number of terms, then we're going to let n approach infinity. That's just a fancy way of saying that n is going to be a really big number. We can make it a trillion or a quadrillion or a trillion to the trentillionth power. It's going to be a number that is huge. And we're going to rewrite this expression down here. And because n is becoming a really, really big number, r to the n is going to be 0 for all intents and purposes. Because r to the n is going to approach 0 as n becomes really large. So for all intents and purposes, we can just say that because it approaches 0, we can just say that r to the n is going to be 0. That's the idea of a limit. Technically, this expression never equals 0, but we know the limit is 0 as n approaches infinity, as n gets really big. So we can just say that the limit is 0. And so we take this expression here, rewrite it, but because n is a huge number, we just say that r to the n is 0. And again, remember, r is a fraction. This only works if r is a fraction. So if we have 1/2 times 1/2 times 1/2, the expression just gets smaller and smaller and smaller. R to, let's say r is 1/2. 1/2 to the second power is a lot bigger than 1/2 to the 100th power. And if we let n be 1,000, this is going to be even smaller and smaller, and we're just going to let that expression be 0 because we're allowing n to approach infinity. So that means that this fraction disappears, and we're left with this fraction, and that's the formula for the sum of an infinite geometric series. So again, we use the idea of a limit, which we're going to explore much more in depth in the next course, calculus. So again, get a picture of this formula, and let's try some problems. So it says, find the sum of all of the terms in each geometric sequence. So again, this ellipsis tells us that the sequence continues indefinitely. So there's an infinite number of terms. So we're going to use our formula. Now, technically, we need to confirm that the common ratio is a fraction between -1 and 1 before we do this. So the first term times the common ratio has to be equal to 1/2. And again, we know these are geometric sequences. They tell us that. So if you solve, r is equal to 1/10. So this is definitely between -1 and 1. So we know our formula is going to work. So the sum is equal to the first term over 1 minus the common ratio. The first term is 5. The common ratio we found was 1/10. And so we get 5 over 9/10, and there's a number of different ways to simplify this. The easiest way, the fastest way, is to multiply both sides of the fraction by 10. But if that confuses you, you can just consider this fraction line to be a division operation. So we have 5 divided by 9/10, and that's just basic arithmetic. We get 50 over 9. So we added an infinite number of terms to find the sum of all of the terms in that geometric sequence. So I know that that seems impossible, but again, with the concept of a limit, we were able to do that. So let's make some more room here. We'll show that we found that the common ratio is between -1 and 1. Oops, that should be 1/2. So R is 1/10, and 1/10 is less than 1, but it's greater than -1. So we showed that we can find the sum of the infinite geometric series. So let's try another one of those problems. So again, let's first show that we can find the sum. So -1 times R should be equal to the next term. The first term times the common ratio is equal to the second term, and so the common ratio is -4/5, and -4/5 is between 1 and -1. So that means we can find the sum. Let's use our formula. So the infinite sum of a geometric series where R is between -1 and 1 is equal to the first term of the series, which is -1. I got that from here, divided by 1 minus the common ratio, which in this case is -4/5. Let's make some more room. And so we have -1 over 1 plus 4/5. And that simplifies to -1 over 9/5. And there's a lot of different ways to simplify, but you should get -5/9 as your final answer. So again, we added an infinite number of terms. Okay, so let's go on to the next sequence, and we have a purple star, which tells us that something different is going to happen here. Let's confirm that the common ratio is between -1 and 1. So we'll take the first term and multiply it by the common ratio, and we should get the second term, 0.33. And if we do the math and divide 0.33 by 0.3, we get 1.1. And notice that 1.1 is not between -1 and 1. So we can say, because 1.1 is not between -1 and 1, the sum does not exist. And we can make that our answer. So what this means is that these numbers are just going to get bigger and bigger and bigger, and so the sequence is not going to approach 0. In order for us to find an infinite sum, the terms have to approach 0, and that's not the case here, so we can't use our formula. If we use this formula, we're going to get a number that doesn't really represent the infinite sum. Okay, so let's do one more of these problems. First, we have to confirm that r, the common ratio, is between -1 and 1. So if we take the first term and multiply it by r, we should get the second term. And if we do the math on that, we end up with 0.7. And 0.7 is between 1 and -1. So we can use our formula. So the infinite sum is the first term divided by 1 minus the common ratio. That's our formula. The first term is 0.5, and the common ratio is 0.7. So we have -0.5 over 0.3, and if we multiply both sides of the fraction by 10, we get 5 over 3. That's just one way to simplify. So that is the infinite sum, the sum of all the terms. So I want you to take a picture of all the work that we did here to help you, and go ahead and try number 13. You probably want to confirm that r, the common ratio, is between -1 and 1 before you try to find the sum, because remember, you cannot use this formula unless the common ratio is between -1 and 1. So try 13. When you come back, we'll do it together. Okay, we're back. So if we multiply the first term times the common ratio, we should get the second term, which means that r must be equal to 1/5. And 1/5 is between 1 and -1. That is true. So that means that the terms are approaching 0, and we can use our formula for the sum of an infinite geometric series. The first term is 10. I got that from there. The common ratio is 1/5. So we have 10 over 4/5. Multiply both sides by 5, and we get 50 over 4, which is 25 over 2, which is 12.5. So if you got that right, excellent. Go ahead and try number 14, and when you come back, we'll do it together. Alright, we're back. So let's first confirm that the common ratio is between -1 and 1. If we take the first term, multiply by the common ratio, we should get -3/2, the second term. So if we solve for the common ratio, we get +3/4. So +3/4 is between 1 and -1. So we can find the sum. So the sum is equal to the first term divided by 1 minus the common ratio. The first term is -2, and the common ratio is 3/4. So we have -2 over 1/4, which simplifies to -8. So Have you got that right? Excellent. Go ahead and try number 15, and when you come back, we'll do it together. Okay, we're back, so let's confirm that the common ratio is between -1 and 1. If we take the first term, multiply by that common ratio, we should get the second term, and if we solve, we get -5. Now, -5 is not between -1 and 1. So, because r is not between -1 and 1, the sum does not exist. So that is our answer. What this means is that the terms just keep getting bigger and bigger and bigger, and because the terms do not approach 0, there's no way that you can find the sum, because it's what we call a divergent series, meaning it doesn't the sum doesn't really approach any number. It just goes off into infinity. Okay, so if you got that right, good job. And you can say r, or you can say -5. Because -5 is not between -1 and 1, the sum does not exist. Okay, so I want you to try one more of those, and when you come back, we'll do it together. Alright, we're back, so let's confirm that the common ratio is between -1 and 1. So the first term times r should be equal to the second term. So if we do the math, we get 0.25 for the common ratio, or -0.25. And -0.25 is between 1 and -1. So we can use our formula, and I'm going to go up here. The infinite sum is equal to the first term divided by 1 minus the common ratio. The first term is -0.5. The common ratio is -0.25. So we have -0.5 over 1.25. And if we do the math on that, we get 0.4. So the infinite sum is 0.4, well, technically -0.4. So there you go. If you got that right, excellent. So now we're going to learn to work with expressions for the nth terms of sequences. You can represent a sequence with a list, as you see here, but you can also represent it with an algebraic expression like you see here, and it's actually easier to represent sequences with algebraic expressions. It's also more exact because we don't have to use inductive reasoning if we have an expression. I know what every single term in the sequence is just by looking at that expression, but looking at these first three terms, we have to use inductive reasoning. We have to assume that the pattern continues the way that we see it here. So let's do some problems. It says write the first three terms of each sequence written below, and we're assuming that the first term is produced when n equals 1. So here we have an expression, and notice we have braces around this expression. That shows us that this is not just an algebraic expression, it's something representing a sequence. So we want to find the first three terms. So what we do is we plug in 1 for n. Why 1? Well, because they told us that the first term is produced when n equals 1. So then we plug in 2, and then we plug in 3. So we have the first term, the second term, and the third term by plugging in 1, 2, 3, and we just keep plugging in those positive integers. That's how sequences work. So the first term is going to be 0, the second term is 3, and the third term is 8. So it is possible for a term to be 0. So those are the first three terms of that sequence. Now over here we have cosine, so we're going to plug in 1. We always plug in 1 first, and then 2, of course, and the subsequent positive integers. And we could use a calculator with radians whenever you define some sort of a trigonometric function. It's always important to mention if you're going to use degrees or radians. So in upper math courses, typically we use radians. But if we calculate these expressions, they're going to be irrational numbers, or decimals that go on forever, that are non-repeating and non-terminating. So it's better to just leave the first three terms in that form. Okay, so let's find the first three terms of this sequence. So we're going to plug in 1, and we'll plug in 2, and we'll plug in 3. So those are the first three terms. So we have 1/2, 1/4, and 1/6. Okay, let's try another one. So to find the first term, we plug in 1 for n. And to find the second term, we plug in 2 for n. And to find the third term, we plug in 3 for n. So we have 3 plus 1, 9 plus 8, and 27 plus 27. So the first term is 4. And the second term is 17. And the third term is 54. So again, we're just learning how algebraic expressions can be used to define sequences. So I want you to try number 21. And when you come back, we'll do it together. Alright, we're back, so I'm going to plug in 1 to get the first term, and then 2 to get the second term, and 3 to get the, the third term. So 4 is the first term, 9 is the second term, and 14 is the third term. So if you got that right, excellent. Alright, let's try 22. Go ahead and attempt 22. When you come back, we'll do it together. Alright, we're back. So I'll plug in 1 to find the first term, 2 to find the second term, and 3 to find the third term. The square root of 1 is 1, so you can write the first term as 1. So if you got that right, excellent, good job. Go ahead and try 23. When you come back, we'll do it together. Okay, we're back. So we're going to plug in 1 to find the first term. You plug in 2 to find the second term. And we'll plug in 3 to find the third term. So we could use a calculator to find decimals for our answers, but those decimals would be difficult to deal with, so you don't have to do that. Okay, go ahead and try number 24. And when you come back, we'll do it together. Okay, we're back. So we're going to plug in 1 to find the first term, and then we'll plug in 2 to find the second term, and we'll plug in 3 to find the third term. And so let's make sure that we did all that correctly. Everything looks correct. So we have 4 over 3 plus root 2, that's the first term. We have 4 over 4 plus root 4, that's the second term. And 4 over 5 plus root 8, that's the third term. So there's really nothing we can do with the first term. We can just rewrite it. We have 1 plus 2. 4 over 4 is 1. Square root of 4 is 2. And we have 4/5 plus. We can pull out a perfect square. 8 is 4 times 2. The 4 comes out as a 2. The other 2 stays in. And let me move this down a little bit. You don't have to show every one of these steps, but we're just taking it slow. Second term is 3. So those are the first 3 terms, if you got that right. Excellent. So we were given an expression for the sequence and asked to find the first 3 terms. Well, now we're going to go backwards. We're given the first 4 terms, and we're going to be asked to find an expression, an algebraic expression for the sequence. And we need to identify whether or not the sequence is arithmetic or geometric. You can see that this is a arithmetic sequence. We're adding 2 each time. So let's first write arithmetic. That's part of the answer. So that's step 1 of the problem. Step 2 is to find an expression. And you may be able to do this by using trial and error, but we can always use our formula for the nth term of an arithmetic sequence. So if you recall, we learned these formulas in the previous class. So those are the formulas that we're using. Let me move them down here. So we're using this formula here for finding a term in an arithmetic sequence. And so the first term is 5. The common difference is obviously 2, but we're just leaving n. And so we're going to use the distribution property, and we get 2n minus 2. And then 5 minus 2 is 3. So we have our expression for the nth term of a sequence. And because we're used to writing those expressions in braces, I'm going to write the final answer in that form. You could write the nth term in this form, but mathematicians prefer this way because you don't have to write the equal sign in the a subscript n. So now we have an expression for that sequence. If you plug in 1 for n, you get 5. If you plug in 2 for n, you get 7. If you plug in 3 for n, you get 9. and so on and so forth. Let's try another problem. So we can see that this is obviously a geometric sequence because we're multiplying by 1/3 to get the next term. Now the nth term of a geometric sequence is equal to the first term times the common ratio to the n-1 power. Now if you forgot that, again, we learned that formula in the previous class. So the first term is 9. The common ratio we can see is 1/3. And that's about it. You could simplify this a little bit, but it would just complicate things. It's not really necessary. So I'm going to use braces to write the final answer. And there you go. So that's an expression that tells us exactly what the sequence is. If you plug in 1, you get 9. If you plug in 2, you get 3. So on and so forth. You can change the form of this by converting 9 to 3 to the second power and doing some algebra there with the exponent rules. But again, there's no need to complicate things. That's not the point of this class. Alright, let's try a couple more of these. We have another arithmetic sequence. So that's step 1. We have to identify the type of sequence. Step 2 is to find the nth term, or write an expression representing the sequence, which we call the nth term. And we're going to use our formula for the nth term of an arithmetic sequence. The first term of the sequence is 56. The common difference is -7. And so the nth term is equal to 56 minus 7 times n-1. I'm showing a lot more work than you really need to show. We're going to use distribution. And we get 63 minus 7n for the nth term. And we're going to use braces for the final answer, because the braces show that we're representing a sequence. This represents a sequence also. But again, mathematicians just prefer to write it in this form sometimes. Alright, let's try one more of these. This is a geometric sequence because we're multiplying by -2 each time. And the nth term of a geometric sequence, if you recall, is the first term of the sequence times the common ratio raised to the n-1 power. The first term is -1. The common ratio is -2. And that's about all we can do. So all we have to do at this point is write the expression in braces. And there you go. So I want you to use numbers 25 through 28 to do number 29. Determine if it's an arithmetic or geometric sequence, and then use your formulas to find the nth term, which is an expression representing the sequence, an algebraic expression. So see these yellow formulas, those are geometric formulas that we use, and the arithmetic formulas are these blue formulas. So try number 29. When you come back, we'll do it together. Alright, we're back. So this is a geometric sequence. And the nth term is given by this equation here. The first term is 1. The common ratio looks to be 5. And so the nth term is equal to 5 to the n minus 1. And let's write it in braces. And there you go. That's an expression representing the sequence, an algebraic expression representing the sequence. So if you got that right, excellent. Go ahead and try number 30. And when you come back, we'll do it together. Okay, we're back. So this is an arithmetic sequence. And the nth term of an arithmetic sequence is given by this formula here. The first term is -6. The common difference looks to be -4. And again, I'm going very slow here, but you can skip this step really, or this step, depending on how you want to do it. So we're going to use distribution. And so the nth term is equal to -2 minus 4n. And so we can use brackets to write our final answer, or excuse me, braces, not brackets, braces. So if you got that right, excellent. Okay, go ahead and try number 31, and when we come back, we'll do it together. Alright, we're back. So it's kind of hard to see exactly what this is going to be. Let's try subtracting 7.4 from 8.61. We get 1.21. So if we subtract these, 9.82 minus 8.61, we get the same number. So it looks like this is going to be arithmetic. So again, we subtracted these, we got the same number, so it's a common difference. So this is an arithmetic sequence. Now, if we multiply 7.4 by some number to get 8.61, you would get an irrational number. So that's probably not gonna be a geometric sequence. And whatever that number is, if you try to multiply it by the second term to get to the third term, it's not going to work. You're not going to get the third term. So we know it's not a geometric sequence. So the nth term of an arithmetic sequence is equal to the first term plus the common difference times the number of terms, or the number of the term that you're looking for, minus 1. So first term is 7.4. The common difference is 1.21. And so we get 7.4 plus 1.21n minus 1.21. So 7.4 minus 1.21 is 6.19. And we can write that in braces. And that is the answer. So if you got that right, excellent. Okay, go ahead and try 32. And when you come back, we'll do it together. Alright, we're back. So, again, you have to do some work to figure out if this is geometric or arithmetic. If you find the difference between these two, you get 3.3, but then if you add 3.3 to 6.3, you don't get 13.23, so it's not an arithmetic sequence, it's got to be geometric. So it looks like we're multiplying by 2.1 each time, but if you have any trouble figuring that out, you can just multiply the first term by r, and you should get the second term, and then solve, and then we see that 2.1 is going to be the common ratio. So if you multiply this term by 2.1, you get that term, and so that shows that it's a geometric sequence. So the nth term of a geometric sequence is given by the following formula. The first term is 3. The common ratio we said is 2.1, and that's really all you can do. So let's use braces to write the final answer, and there you go. So if you got that right, excellent. Okay, so in the previous problems, every sequence that we defined with an algebraic expression was either an arithmetic sequence or a geometric sequence, but these sequences down here are neither. But we're still going to find an expression for the nth term. So this one's pretty easy. It's just 1 over n. Plug in 1, you get 1. Plug in 2, you get 1/2. Plug in 3, you get 1/3. Plug in 4, you get 1/4. Now I want to clarify, the denominators do display an arithmetic sequence. You're adding 1 each time, but because they're the denominators of a fraction and the numerators don't change, technically this is not an arithmetic sequence. So it's a little deceiving, because again, the progression of the denominators does display an arithmetic sequence. It's an arithmetic progression, but it's not an arithmetic sequence. So here we have the same thing. We're going up by 1 each time in the exponents, but we're starting at 2. So how do you, if we started at 1, we would just write pi to the n power. But because we're starting at 2, we write pi to the n plus 1 power. And the reason that works is because if you plug in 1, you get 2. If you plug in 2, you get 3, and so on and so forth. So that is an expression describing the sequence. As long as we know that we always start with n equals 1, which we're told up here, then we have an expression that completely describes the sequence. So let's try number 35. 35 is pretty much the same type of problem, but we're starting at 5, so we have to write n plus 4 in our exponent. So if you plug in 1 for n to get the first term, then you get 5. If you plug in 2 for n to get the next term, then you get 6, and so on and so forth. Let me draw that a little nicer there. So that is the answer. Now if you're wondering what E is Euler's number. That's just a constant. So we don't really have to do anything with that. So let's try one more of these. Now this is a challenge problem, and I want you to realize that these expressions can be pretty complex, and it becomes very difficult to come up with the expression in certain with certain sequences. But when I give you a challenge problem, I'm always going to give you a hint because I don't want to make things unnecessarily difficult for you. We're told that n to the third power is going to be part of the expression. And that makes sense because these numbers are growing pretty quickly. So if we write n to the third power, we plug in 1, we get 1. Plug in 2, we get 8. Plug in 3, we get 27. Well, we're not getting those numbers. We're getting actually 3 less than those numbers. So it's going to be n cubed minus 3. Now if you plug in 1 for n, you get negative 2. If you plug in 2 for n, you get 5. Plug in 3 for n, and you get 24. Plug in 4 for n, and you get 61, so on and so forth. So that was kind of a challenge problem. But again, I'm always going to give you a hint to help you. Okay, so I want you to try number 37. And when you come back, we'll do it together. Okay, we're back. So we have log base 2 of n, and that's it. It's that simple. So if you got that right, good. Go ahead and try number 38. When you come back, we'll do it together. Alright, we're back. So we can see it's just going to be e to the n over square root n. If you plug in 1, you get e. If you plug in 2, you get this term here, and so on and so forth. So if you got that right, excellent. Try number 39. Number 39 is going to be a little bit more difficult, but see if you can do it. And when you come back, we'll do it together. Okay, we're back. So the numerator displays an arithmetic progression starting at 3. So when you plug in 1, you're going to get 3 in the numerator. Plug in 2, you get 4 in the numerator. Plug in 3, you get 5 in the numerator. Now the denominator is displaying an arithmetic progression where you're adding 1 each time. But you're starting at 4, so we're going to write n plus 3 in the denominator. Then if you plug in 1, you get 4. Plug in 2, you get 5, so on and so forth. So things get kind of complicated when the fractions are reduced, because then you can't see the progression. But in this case, none of these fractions have to be reduced, so we can kind of see what the pattern is. And be aware that we are using inductive reasoning, so we don't know for sure that this describes this list of numbers, but inductive reasoning is a pretty powerful way of reasoning, so we just assume that this describes the sequence completely and accurately. So if you had trouble with that, that's okay, because that one's a little bit more difficult. Now, this is a challenge problem, so I give you a hint. So try number 40, and when you come back, we'll do it together. Alright, we're back. So we know that n squared is going to be a part of the expression. If you plug in 1, you get 1. If you plug in 2, you get 4. If you plug in 3, you get 9. If you plug in 4, you get 16. So you can see what's happening here. We're just 1 more than the result after we square. So n squared plus 1 is going to be the expression we're looking for. So if you got that right, good. Okay, so now we're going to learn something called recursive form. We're going to find the nth term, an expression for the nth term of a sequence, just like we did in the previous problems, but we're going to write the nth term in something we call recursive form. So recursive form is an equation that shows you how to find a term in a sequence using the previous term. So for example, if we want to describe this sequence here, we can use explicit form, and the reason we call it explicit form is it shows us very plainly how to find each term. This is the form that we've been using in previous problems, but we can also use recursive form. And notice that we have an arithmetic sequence here. We're adding 2 to get to the next terms. So recursive form tells us if we want to find a term in the sequence, we take the previous term and add 2. So a subscript n minus 1 is the previous term. Now, be aware this is a subscript, so don't be confused by that. A n minus 1 is one number. That's all one number. And a n is one number. So again, if you want to find a term in the sequence, you take the previous term and add 2 in this particular case, because we're adding 2 to get each term. Now, recursive equations don't really describe sequences completely because there's no reference point. So typically when you're given recursive form of the nth term of a sequence, you're given one term in the sequence, and that term is typically the first term. So this gives us a reference point. Here's another example of a geometric sequence. And this is explicit form, which we wrote in previous problems. Recursive form tells us if you want to find a term in the sequence, you take the previous term and you multiply by 4. Because we're multiplying by 4, that's the common ratio in this particular sequence. So it's just a different way to write the nth term of a sequence. So let's try some problems here. It says write an equation of the nth term of each sequence in recursive form, and also show the value of the first term. So it looks like we're adding -4 each time, or you could say we're subtracting 4. This is actually a sequence that we saw previously. So to find a term in the sequence, you take the previous term and you subtract 4. And that's it. But we need some sort of a reference point. So it says show the value of the first term also. So the first term, a1, is -6. And we'll put a comma in between our equations. So I'm going to use brackets. Typically you don't really see, or braces, that is, not brackets, braces. Typically you don't see braces with these types of expressions, but it's probably best to write them just to show that you're defining a sequence. Okay, so that was an arithmetic sequence. Let's try the next problem. So a1, the first term is 1, and to find a term in this sequence, you take the previous term and you multiply by 5. So that's what a geometric sequence looks like when it's written in recursive form. Alright, let's try a couple more of these. The first term, we're always supposed to write the first term, given those directions. The first term is 7.4, and use a comma. And in recursive form, we show that to find a term in the sequence, we take the previous term and we add 1.21. I think that's the common difference for this particular sequence. I think we found that this was a arithmetic sequence. Again, these are all sequences that we saw previously in this class. We're just writing them in a different form. So in 44, I think this was a geometric sequence, and we multiplied by 2.1. So in recursive form, we write the first number, the first term of the sequence, and the nth term is equal to 2.1 times the previous term. So there you go. Okay, so see if you can write some sequences in recursive form. Remember, you always have to have that reference point, which is usually the first term, and we're asked specifically to write the value of the first term. So try number 45. When you come back, we'll do it together. All right, we're back. So the first term is 2, and any term in the sequence can be found by taking the previous term and adding 2, because this is a arithmetic sequence. So if you got that right, excellent. Go ahead and try 46. When you come back, we'll do it together. All right, we're back. So the first term is 9, and any term in the sequence can be found by taking the previous term and multiplying by 1/3. You can also write a subscript n minus 1 over 3. It's the same thing. So if you got that right, good. Okay, go ahead and try number 47, and when you come back, we'll do it together. All right, we're back. So the first term is 56. Any term in the sequence can be found by taking the previous term and subtracting 7. So if you got that right, excellent. Try number 48, and when you come back, we'll do it together. All right, we're back. The first term is -1, and any term in the sequence can be found by taking the previous term and multiplying by -2. So if you got that right, excellent. Now, you could write the previous term first and then multiply by -2, but this would look very clumsy and very sloppy, and there'd be a lot of room for misunderstanding and confusion. So it's just traditional to write the common ratio first. Okay, so that was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1, number 2, 3, 4, 5, 6, 7, and 8. But don't go before you get the homework. here's screenshot number 1 of the homework, and number 2, and 3, and 4, and you have the answers at the right. So be sure to check all of your answers. If you do a problem and they don't check your answer, that means that you just wasted your time doing that problem. It's not enough just to attempt the homework, it must be done correctly. So get that homework done. Be sure to keep it in order in your binder and write neatly. And I'll look forward to seeing you in the next class.